I am Dr. Juluru Sandeep, Assistant Professor, Department of Aeronautical Engineering, Institute of Aeronautical Engineering College. Today, I am going to discuss about the well-posed problems from computational aerodynamics and turbulence modeling subject. This particular concept covers CO3. Select the quasi-linear partial differential equations for estimating the behavior in computational fluid dynamics. So we have discussed about how the partial differential equation, the governing equation of the fluid flow behavior is going to affect the CFD approaches. So we have differentiated the PDEs into elliptic, parabolic, hyperbolic based upon the roots of the characteristic lines or based upon the eigenvalues. And also we have seen some of the examples how different flow problems which have been defined by the different governing equations are having the different form of the behaviors. So as we have seen for the hyperbolic form of equations, we have the two elliptic, two characteristic curves, and parabolic one characteristic curve, and the elliptic does not have any characteristic curves. So and we have also discussed the approach when we have the hyperbolic form of behavior. We are going to define the one boundary condition, so based upon which the solution is obtained, whereas for the parabolic we are defining the initial conditions and the boundary conditions, and for the elliptic form of equations we need to define all the boundary conditions. So for any given fluid flow problem, we have to define the governing equation, we have to define the boundary conditions, we have to define the initial conditions, we have to define the mesh or the grid, and we have to define the material properties, and we have to define the numerical method. So then only the solution can be obtained. So if you are going to define the different boundary conditions with respect to the behavior of the equation, so then it may lead to the divergence of the solution. We cannot get the correct solution, or the numerical iterative method cannot process for the further iterations. So the solutions we are going to obtain by some numerical methods may not give the accurate solution. So it may give some results, but they may be having some error, or they may be having some different flow which is not required. So this is caused because of the inaccurate boundary conditions, or insufficient boundary conditions, or the initial conditions, or maybe the mesh which has been defined, or maybe the material properties which we have defined. So there may be so many causes which defines the problem setup as a ill-posed problem. So the problem which we have defined will be denoted or will be indicated as an ill-posed problem, because it is giving you spurious results at best, or the no solution, or the worst solution, or the high percentage of error in the solution that we can consider. So a simple example, we can consider the supersonic blunt problem when considering the subsonic supersonic flow for a steady flow point of view. So any attempt made to obtain the solution will lead to the ill-posed problem. As we know, the supersonic problem considers as a hyperbolic behavior. So where we need to define the initial conditions or boundary conditions to obtain the solutions. But once it becomes into subsonic, then the boundary conditions are not enough to solve that particular problem. So such that it becomes an ill-posed problem. So this type of solution leads to a divergent solution. So here a simple graph which is showing you from the ANSYS fluent. So this is different equations that are solved with X momentum, that is X velocity, Y momentum, Z momentum, and the continuity equation, and the energy equation, and turbulence characteristics with K and epsilon. So the X-axis is showing you the number of iterations okay, and the y-axis is showing you the residuals for each governing equation. So when all the equations are dropping based upon the number of iterations, then we can consider it as a divergent solution. But here, after some iteration, it is increasing, the residuals are increasing, which means that it is a divergent solution, which is considered as an ill-posed problem. That means the given boundary conditions or the initial conditions are not enough to solve the given problem. So this causes the ill-posed problem. So then what is well-posed problem? So if the solution to a partial differential equation exists and it is unique, and if the solution depends upon the initial and boundary conditions, then the problem we call it as a well-posed problem. So in CFD simulations, it is very important to establish the problem as well-posed problem before getting the numerical solution. So as seen, when the blunt body problem was set up using unsteady Euler equations and a time marching procedure was employed to go to the steady state at larger times, starting with essential arbitrary assumed initial conditions at time t equal to 0 is considered as well-posed problem. But after some time, when it comes to the shock formation blunt, or when it comes to the subsonic region, so in that case, the well-established boundary conditions will define it as a well-posed problem. So comparing the well-posed and ill-posed problem, we can see some of the aspects, how it is going to differentiate, or how we can understand the difference between the two cases. So solution existence is S for the well-posed problems, and for ill-posed problems, the solution may not exist. And uniqueness, yes, we have the uniqueness in the well-posed problems. In ill-posed problems, it depends upon the error which we are going to obtain and the problem setup which we are going to define. It will be having the multiple solution. And sensitivity to input, so it is very small in case of the well-posed problem, but in case of ill-posed problems, it may lead to huge changes in the solution. So example, we can consider the laminar pipe flow, and in the ill-posed problem, we can consider the backward heat equation. And the typical partial differential equation types for well-posed are elliptic, parabolic, and hyperbolic. And for ill-posed problem, it is a misdefined or ill-conditioned problems we can consider. So let us see some of the cases where we are in general, we come across while solving the fluid flow problems. What mistakes leads to the ill-posed problem, or what mistakes leads to the divergence of the solution. Generally, many researchers do the ANSYS fluent simulations for the CFD problems. So let us go with some case where we use the ANSYS CFD to understand the ill-posed and the well-posed conditions. So here, as we know, the rules of thumbs for the each and every governing equation, that is, the elliptic requires all the boundary conditions, whereas parabolic requires the initial conditions and boundary conditions, whereas hyperbolic requires the initial or the boundary conditions are enough to solve the solution. So here I am taking an example for simulating the supersonic flow in an intake for a scramjet or a ramjet engine. So here it has the ramp walls. We have defined the boundary conditions. This is a ramp and this is a ramp, and this is the isolator wall, and this is the cowl wall, and this is the pressure outlet, and this is the pressure far field inlet and pressure far field free condition. So as we know, the fluid is coming from this particular direction. So we have defined this face as an inlet, and we are doing only 2D analysis. Okay. So such that we have given this line as outlet, and all other lines, curves with respect to the condition, with respect to their functioning, we have defined these as no slip walls. So all the solid geometry will be considered as no slip wall. So with respect to the given dimensions, we have defined the domain of the fluid flow. Okay, so if you are going to define here in place of wall, this as a inlet, okay, and this as a wall, and so the fluid cannot exactly simulate the required flow physics. So because once the flow starts here, supersonic flow, here we'll get some shock waves. So we have to capture the reflection of the shock waves and how the flow is passing through that particular intake. So for this case, the boundary conditions which we are going to define, or the boundaries which we are defining. So if you are defining it an inappropriate boundaries, it may lead to some ill-posed problem. So as we said, it is a two-dimensional problem. So if the two-dimensional problem has been imported to three-dimensional solver, then it may lead to the wrong dimensions. Okay, so this is the one of the problem mostly people do without basic knowledge of the what type of problem they are going to solve, either 2D or 3D. So that is the one way how ill-posed problem has been defined. So and next one, this is the general procedure we follow in the fluent ANSYS. First, we are going to define the problem, whether it comes under the laminar flow or turbulent flow, compressible or incompressible. So if it is a multi-phase flow, we are going to take the multi-phase option. Based upon that, different materials can be chosen. And if it is a compressible flow, we take the energy equation. So without which we cannot solve the shock problems or the high speed flow problems. So and if it is the turbulent flow, then we have to choose the K epsilon, K omega or SST models. And if it is a laminar flow, directly we go with laminar. And if it is a combustion problem, we have to take the species, fuel species, what is the fuel. And if it is a noise problem, we take the acoustics. So like based upon the problem which you are going to solve, you have to choose the model to solve that particular problem. So if it is an incompressible flow, if it is compressible flow and you are not choosing the energy equation, then it leads to an inaccurate solutions. So always the compressible flow problem needs the energy equation to get the solution. And similarly, here you have the material properties, air, okay, and the boundary conditions and the solution methods, solution initialization. If you are not defining any particular point correctly, then it may lead to the divergent solutions in the process. So in the material properties, so for the compressible flows, we take the density of air as ideal gas. If it is an incompressible flow, then we take the density is constant. And you can also add the different materials if required. You can take the medium as liquid or any fuel. So based upon the inbuilt database you can define, or you can go with the user database where you can define your own material. So like similarly here you have the viscosity. So whether viscosity varies with Sutherland's constant or thermal conductivity, specific heat. So all these will give you the exact flow what is to be solved in the given problem. So similarly, as said, the boundary conditions plays a vital role in the obtaining a convergent solution. So whether you have defined inlet, so whether the inlet is velocity inlet or mass flow inlet or the pressure far field. So because each boundary will have the different initial conditions. So for example, you are taking the velocity inlet where you have to define the velocity, pressure and other parameters. So if it is a pressure far field, you can define the pressure, Mach number, X component, Y component. So if it is a mass flow inlet, then you have to define the mass flow. So like this, each boundary which we are going to define may have the different initial conditions based upon the given input and based upon the problem which you are going to solve. You can choose one particular boundary condition so that the solution may converge very easily. So similarly, if you have some symmetry problem, so you can define that boundary as symmetry. So if you have some axis symmetry problem, then you can define any particular wall as axis. Okay. So, and if you have some wall, so wall can be no slip wall or imaginary wall, you can give it as a free slip wall. So like this, if you are simulating some wind tunnel problems, then the domain which is going to solve the problem should be have considered as a no slip wall. So if you are solving any problem which is in atmosphere, real flow conditions, then you can consider this as a free slip condition. So then we can get the more accurate results what is required. So like that, based upon the problem, the solution may get converged. So in this graph, on the x-axis it is showing the number of iterations, and y-axis it is showing the residuals of the different equations. So up to 200 number of iterations, we can see all the graphs, all the curves are decreasing, and they are reaching the residual convergence criteria. So in that way, these we can consider this type of graph will defines the problem is a well-posed problem. So if the graph is diverging, then we can consider it as an ill-posed problem. So if at all you are come acrossing such type of divergence, then immediately you have to stop simulations and you have to change your boundary conditions, or you have to change your numerical method or any material properties or turbulence model. So you have to verify each and every step which you have gone through the procedures. So defining the problem, if you are giving some input, definitely it will give you some output, but that input should be correct to get your exact output. So like if you are giving some garbage input, you are going to get the garbage output only. So CFD is considered as a computational fluid dynamics, but some people say it is a colorful dynamics because it is giving you the results in different colors. But interpreting that results as per your requirement, whether the results are coming you the required, just colorful results are not correct, accurate. So you have to understand the results, you have to take that results as per your requirement. If that streamline path, or if that pressure contour, or if the Mach number contour is not showing you what is the lift or what is the pressure difference which you are getting, so then that is not a well-posed problem. So that is the about well-posed or ill-posed problem. So the present content has taken from the computational fluid dynamics, the basics with applications by J.D. Anderson, and also from the Answers Fluent tutorials. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.